In this session, we will introduce some features of HMM and different types of HMM. Key points of HM model lambda have two kinds of procedures. Evaluation and decoding procedures aim to find the conditional probability PO lambda and the possible hidden state when model lambda and observation O are given. Such kinds of procedures belong to inference and can be processed by DP, dynamic programming algorithm. Learning procedure aim to estimate model lambda when observation O is given. It belongs to parameter estimation, which can be processed by EM, expectation maximization algorithm. DP, dynamic programming, and EM, expectation maximization, are two main algorithms used in HMM, which is in essence a generative model. HMM parameter learning can be supervised or unsupervised. In supervised learning, training data includes observation sequence and state sequence. The learning of HMM is very simple. Considering manual labeling of training data is often expensive, we could use unsupervised learning, in which training data has only observation sequences. Under no labeling conditions, HMM learning method needs to use the EM algorithm, including two steps, E step and M step. Since there are hidden data in the given data that have not been observed, it is necessary to guess the hidden data and then find the model parameters. There are different kinds of optimization criterions for training HM model, such as maximum likelihood, maximum mutual information, minimum discriminative information, minimum imperial error, also called discriminative training, and maximum a posterior. When training HMM, different criterions can be selected under different kinds of conditions. For example, it is difficult to get MLE when there are redundant parameters or missing data in the distribution. Therefore, the EM algorithm is proposed. It aims to divide the process of MLE into two steps. The first step is to find the expectation, that is E, so as to remove the redundancy part. And the second step is to find the maximum value, that is M. EM algorithm is an iterative algorithm improved from MLE. According to the different transition probability metrics, there can be several kinds of Markov chains used in HMM. In the previous part, we assume the most general case of full connected HMM, in which every state of the Markov chain could be reached from every other state in a finite number of steps. For some applications, we will use some special types of HMM. The left-right model is one example, where the state index can only increases or stay the same as time goes on. There are some typical shapes of Markov chains. Figure A is a Markov chain without zero values for the transition probability matrix A. Figure B is a Markov chain with 0 values for A. Figure C and D are two Markov chains in left-right form. According to the different probability of observation, HMM can be classified into three categories: DHMM, discrete HMM, CDHMM, continuous density HMM, and SCHMM, semi-continuous HMM. As to the DHMM, the output probability of each state is distributed according to observation symbols. The output symbols are selected from a limited discrete symbol set according to a certain discrete probability distribution. In speech processing, vector quantization, VQ, is often used to convert each speech feature vector to the form of code word. The output probability is carried out on the code word, which can be regarded as discrete symbol set. VQ quantization errors, discrete HMM will affect the recognition rate, but has small calculation. GMD-CD-HMM is a kind of continuous density HMM model commonly used in speech recognition. The output probability is a probability density, not a matrix. The probability distribution of the observation vector is described by Gaussian mixture density, GMD. When the mixture number is large enough, GMD can describe the probability density of the future vector more accurately, and the probability density can be estimated by the EM algorithm. SCHMM combines the advantages of discrete HMM and continuous HMM. It is equivalent to a mixture of DHMM and continuous CDHMM. The feature vector of the state output is continuous, and the weighted sum of multiple Gaussian distribution is also used to approximate the probability distribution function. But the set of Gaussian functions used for the weighted sum is fixed. Similar to the establishment of a codebook for the Gaussian density function, the difference between the output probability density of each state is the weighting coefficient of each Gaussian density function in the codebook. HMM can be applied in many fields, where the goal is to recover a data sequence that is not immediately observed, but other data that depend on the sequence are visible. In robotics, human-robot interaction, common usage include speech recognition, synthesis, and tagging, natural language analysis, machine translation, handwriting recognition, time series analysis, activity recognition, sequence classification, and so on. In speech recognition applications, HMM problem is how to predict the original text information through the given speech signal. Here, the acoustic signal is the observation state. The recognized text, phones, syllable, words is the hidden state. Speech synthesis is the inverse process of speech recognition. In application of handwriting recognition, the observations are image or stroke sequences. The hidden states are words by handwriting. Text mining includes different researches like information extraction, text classification, text clustering, text compression, and text processing. For example, associated rules. In the application of information extraction, the observations are word sequences. The hidden states are word tags. In the application of gesture recognition, the observations are single or multiple data sequences, indicating hand movement. For example, I'm use sensor reading. The hidden states are gesture labels. That's all for this chapter. See you next chapter.